Okay,
I start already. Okay.
okay, okay. Today I will talk about this topic called reference counting. Some people ask me in Discord, is it Objective C or C Sharp or any programming language? And the answer is no, because I will focus on C and C++, where we have to manually do reference counting. But actually, every programming language uh, yeah, every language or framework, they have reference counting built in underneath the language. So the difference is for C as or C++, this kind of low level language, you have to do it manually. But for other I forgot what is the name, managed languages, they will help you do it. For example, you look at Java. Java usually, yeah, there's this concept called pass by reference. Or look at this passing object references. So in Java, just using Java as an example, but this should be the same thing in most languages. So for example, if we have an object foo, then when we call modify and we pass a into foo, you will usually pass the reference of A into modify and not the object itself. If you remember last session, we we looked at some examples where I call malloc myself. Look at these examples. After we call malloc to create an object, if we if we call malloc, it will return a pointer to the object, and then we will use the pointer. We will pass this pointer around if we want to do anything with it. And this is called pass by reference, because we are passing the reference of this object. But if we have thing, if we have a object that is allocated on the stack, oh, I didn't have that demo. If we have an object that is allocated on the stack, meaning that you just do like this. We don't use malloc, we just declare like this. Then the value will be on the stack, and you will hold this as the whole object as a value. Then when we pass this to another function, for example, if we do this versus, we'll delete everything, versus this, see there's error because we need to pass the pointer. So the difference here is this one passes by the whole value. So it will copy this whole struct into here. But this one will just pass the pointer this into here. So let's look at it in GDB. Let me just do something simple. So for pointer, you have to use, we use this syntax, which I showed last time already. So if we compile this one, and then we open inside GDB, then we look at main. Okay, okay, maybe it's hard to see, but when you have, for the first function, it will copy. You see, there are more moves. There are 4 moves. There are more moves because we want to copy the contents in here into, to pass it as an argument into here. So it copies 2 things because there are 2 things here. But when we do this one, you just pass a pointer. So LEA is to get the pointer, get the address. So you see the difference. This one will copy the whole object, all the contents, and this one is passed by value, and this one is passed by reference. Okay, so the point of talking about this is to show the difference first of between passed by value and passed by reference. Now I give another example in Python. So I'll give another example in Python that does pass by reference. So if we have an array like this, okay, this one, let's say this function takes in an array, and then we do something like this. What will happen if we just call the function? It will modify because we are passing the whole reference of this array of this list into this function. Then yeah, because we are passing by reference, that's why when we modify it here, this whole object gets modified. So now the question is, when we have this kind of code and we do initialize a list like this, who will manage the memory for this? Because if you think about it from of the low level details, what happens when we do this is this one will allocate a buffer that stores these values. Then after that, if the program does more things, will this buffer stay in memory all the time? Because if it stays in memory all the time, then your RAM usage will be very high, and usually that is called memory leak. So normally when we write Python programs or Java or C# or any programs, usually the runtime will manage all these allocations for us, meaning that when you don't use this thing anymore, when this object is not used anymore, when object is not used anymore, it will be freed by the runtime or deallocated. So we don't have when we write Python or Java, all these kind of programs in these kind of languages, they will manage the memory allocations for us, and we don't need to do anything about it. We just leave the runtime to allocate and deallocate for us. But now in C, there's no such thing. As you have seen, we have to, if we want to allocate memory, we will allocate it ourselves, and then we have to free it ourselves. For example,
Sorry. Can you enlarge a bit for the font size?
okay. Like this.
It's good now. Thank you.
Okay, so this one is the code that we have seen before. Let me try and move this down. So this one is what we have done before. Then let's say if we allocate 100 of this 1000 or 10,000, then and then we don't do anything. I just use sleep to pretend that the program is doing something else. Okay, then I run it. Okay, then it will sleep for 1000 seconds. But if we look at the memory usage, okay, not so easy to see. Wait, okay, maybe this one is too small. We'll make it bigger. Oh, okay, maybe it's still too small. Yeah. I will run this instead. Okay, this one. See over here, the program is using 10 MB, that's 10,000 KB. It's using 10 MB of memory because we didn't free it because we have just allocated. Now, you see what happens if we free all of them. You see, this time, because we free all of them before sleeping, you see, the memory usage is very low. So that's the difference. That's that's also the reason why you see some of the programs that we run, like Chrome, use a lot of RAM because they have a lot of allocations and they haven't freed them yet. And this is why it is so important for developers to free allocations once they don't use the object. Because if they don't free it, then your memory usage will be very high. Because they are all allocated, then they are all used. So it's important for programs to free memory to keep memory usage low. So back to this managed languages, they will do it for us. They will help us check if the object is still used. If it is not used, then it will free it. So how does it know whether it is used or not used? So this is the now the topic of garbage collection. So Java, Python, they all have their own garbage collector. So they see the garbage collection is the automated process of deleting, so freeing allocations that are no longer used. Python, Java has its garbage collector, then Python also has its own, and then C Sharp also has its own. All of them have a garbage collector, but plain C, because it's a low level language, it has no garbage collector. If you want a garbage collector, you can write your own, or there are implementations such as this that is quite seems to be quite well known. And then in JavaScript also, there is a garbage collector. For example, you look at WebKit, then they have a whole blog post to explain to you how their garbage collector works in the browser for the JavaScript engine. And actually, there are also bugs, vulnerabilities in the garbage collector sometimes. We're not sure if this is a good post, but usually V8 will have they have a few bugs in their garbage collector. So normally these garbage collectors, they are very complex. That's why you see just now there's a very big long blog post to talk about this, and it is a very, very wide topic. But this is quite expensive because you need a whole garbage collector that runs in the background. And what they do is they do this thing called marking. So they will look through all the objects in your program, and then they will mark it. They say, oh, this is still used or this is not used. And then it will iterate through all the uh, children objects that are inside. Then they will again mark it used or not used. So it is actually quite expensive to do this. But in some systems, like the Linux kernel, if they it is too expensive to do, it is very expensive to do garbage collection, and it is nicer to just do reference counting. So Linux kernel and also many other systems, they do reference counting. So now so in today's session, I will go through the concept of reference counting, and then I will end off with a simple example of why this will lead to bugs if not done properly. And then next few sessions, we will look at real world bugs that come from reference counting not done correctly. So now, now that I've gone through the motivation, let's look at the example of how we and why do we do reference counting. So if we reuse this example, you see, let's say if we have a initialization that creates a lot of objects, allocates a lot of objects, and then here we do many things that are related to the program logic. For example, we have something buy, sell car, edit or modify car. Or we have a sell car, or upgrade car. for example. So maybe this is like a game, a code in a game, or in the Linux kernel, yeah, something similar, but that they modify things. For example, file system objects. But we use car as an example. But in Linux kernel, it will be something like file system object, file system handle, things like that. So usually in a program, it will not be so short. There are many things that will happen. For example, maybe like this. Actually, yeah, and also do this. So many things can happen. You can create a car, you can sell a car, and upgrade a car, blah blah blah. But if you write your own program, maybe you don't need to keep the reference for everything because maybe something is not used anymore. Uh, in the future, you don't access the object anymore. Then you can free it already. For example, maybe after you sell a car, after selling, you can free the car. So we do free car. Uh, yeah, yeah. I think of a better example. Okay. Mm, maybe like this. So maybe you you can create 10,000 taxi. We call it taxi lah, better. And then you can enter a taxi and you can exit a taxi. So let's say when all the passengers and the driver has left, exited the taxi, the car, we can deallocate this car. We assume that we don't need to keep this object anymore. But how to know everyone has exited? So now we have to keep track. We have to count how many people are accessing this object. Otherwise, if you see the problem now is you cannot just call free like this because if you got two people that enter and two people that exit, then if we call exit car twice, then this is double free already. Okay, let me call this unsafe exit. Or for example, we have enter car like this, and then someone exit, then another guy enter. This will be used after free, right? Because we already free with unsafe exit. but someone later still uses the accesses it. That, for example, we do printf. If we want to access this object, it is already free. Then it will be used after free. For example, like this. So the safe way to do it is you must count the number of people in a car before you can free it, because otherwise you'll have these bugs. So now let's introduce a reference counter. So let's and we do it like this. When we create a car, we initialize the reference counter to 1. We say there's 1 person in the car. And then when we enter the car, we increment the number of people in the car. Then when we exit the car, if there are no more references, then we can free it. So now let me show print more things so that we can see in a demo. Um, okay, like this. So now we have when we have a safe version, first we set this. Right. Okay, so first, this example, you see when we reach here, then we free again, we get the double free error that we have seen before. So let me comment this out. Okay, now this use after free happens, but it doesn't affect the demo because it, it doesn't crash. But let's look at only this one. So first, we have this oh so I- so enter when we create the reference is one, when we create the reference is one, and then we enter the reference is two, then after we exit reference one, then exit again, reference is zero. And when the reference is zero, we know that no one is accessing this object, then we can free it. So it is a very safe operation because you only free it once, and you only free it when no one is holding to this pointer anymore. So there will be no use after free and no double free. So this is when reference counting is done correctly. Now let me show an example of a bug. So here is a reference counting bug in the Linux kernel, in the IOU ring subsystem. So there is a time when this IOU ring feature is very popular. It's not very, they introduce a new feature, and then it is very popular because there are a lot of IOU ring bugs. You search for, yeah, Starlabs have one write up, then here have one, then here also one. If you search for IOU ring bugs, you can search for find a lot. I think Google doesn't give all of them in this search, but there's maybe 10, 20, or 30, or even more IOU ring bugs. And this one is in reference counting. So just now I say that in this example, I use car as the object, but in the Linux kernel, they will usually be things like file system object. So for example, a files struct. So usually the bug happens like this. It will always be in this kind of pattern. Something doesn't increment the reference counter at one. So over here. So you see over here, this files object is passed, the pointer is passed to here, but the reference counter is not incremented. So I think after all this is just exploit details, but let me show you in our demo here what happens when you don't increase the reference counter correctly. So let's look at this. For example, if when I create a car, I didn't set this to 1. I initialize to 0. And I forget to set this to 1. Okay, for example, I set to 0 instead of 1. So now you see when I have this code, I enter, the reference is just 1. It should have been 2 because I say when we create a car, there is 1 driver inside, and then we enter a car, then there are 2 people inside. But now, because I initialize to 0, the reference is 1, and then when 1 person exits the car, 0, then it just frees the car already. It deallocates already. Then the next time we reach this again, you see this is a use after free. You see this is garbage value because we have a use after free. So This whole bug pattern becomes actually very simple to see. You just count, it is just wrong reference counting. So the when the object is held by another object, we forget to increase a reference counter. And then if you forget to increase once, then the next few times when you decrement, because we are one less than what it should be, then it will you will free one step too early. Then the next time, the one last time that it is accessed, it will be used after free. So when you think about it, the bug pattern is very simple. Just count wrongly. There's another example. Let me get the link. So over here, there's a lot of write-ups for Linux kernel exploits. Okay, this one is is this the same one? Oh, it's the same one. Yeah, I forgot which one I want to show. Okay, I forgot. There was a write-up. I forgot to save the link. So don't have. I will share more about all these real bugs next week, next session. Okay, actually, because every time I hope to end in 1 hour, today we can finally end early. So let's end early today. We try to keep everything below every session below 1 hour. So I think this is a good time to stop. Next session, I will share more examples of all these bugs and a bit about the exploitation details. And then after that, we can also look at the modern programming languages such as Rust. Does Rust have, maybe you all tried before or you all know about it. They have this thing called borrow checker that they make sure that when you actually it doesn't really solve this problem, but you don't need to do reference counting uh, sometimes, but you have to pass this borrow checker thing that makes sure uh, when you pass your values into functions, you maintain the lifetime. So this is called lifetime of the object. You have to maintain the lifetime of the object correctly. That one I will also go into more detail next session. Okay, we can end today early then.
All right. Is there any question? I think no question usually.
Okay, yeah, today quite simple.
All right, then I'll stop the recording.
Okay,